Hi, this is Trevor from Physics This Week. Today we're going to talk about Newton's second law. And by the end of this, you're going to be able to do some simple problems using Newton's second law. And I'm going to show you a few tricks to help you along your way. Okay, Newton's second law tells us that the sum of the forces acting on an object is equal to its mass times its acceleration. And typically, especially in introductory physics classes, you're going to see this as F is equal to ma. Now this is true, but not quite right. Really, you might have an object that has two forces acting on it. So you can imagine force 1 and force 2 acting in opposite directions. If you just add F1 plus F2 without the sign of the vector, you can run into some trouble. So in order to do this, you need to make sure that you specify a direction, and then you're very careful. So instead of writing F equals ma, I like to write F is equal to the sum, or excuse me, the sum of the forces is equal to the mass times the acceleration. And keep that vector sign in there. Now you can break it down into components, and we'll talk about that next. But you want to make sure that you understand completely that it's a vector equation, not an algebra equation, at least not to start. Okay, so you break these into different components, or excuse me, into the different forces. So we've got two forces acting. We've got F1 and F2, so we're going to take F1, we're going to add F2, and those two things together give us this vector equation that the sum of it is equal to the mass times the acceleration. Now I'm going to write it down as an algebra equation, and I'm going to do this in two steps. In the first step, I want to write down F1 plus F2 is equal to ma. Notice that there's no vector signs there, but I'm not going to stop at this point. And typically I would do this in the same step, but I want to show you separately. I'm going to put in plus F1 and plus F2, or excuse me, plus negative F2 to show that direction for F2 is equal to the mass times the acceleration. Okay, so the key part here is this plus sign because F1 points in the positive direction, and this negative sign because F2 points in the negative direction. And I've lifted these up a little bit because I've found it's very helpful to not lose them in the equation if you show them and you don't accidentally miss out on the sign right here in this spot. So this is our algebra equation. And we're going to start out back here with the vector equation. We're going to write this intermediate step. And then you could actually write this plus and minus sign right onto that the first time you write it. You don't have to do these three steps, but I wanted to show you them explicitly there. We're going to put the signs into this vector equation, or this algebra equation, and then we're going to allow the acceleration to pick up the sign from the algebra. Notice I didn't put anything here. In fact, if you're clever, you might notice that the result of these two forces, the net force is going to point back in the negative direction. So I don't put a negative here. I let it pick it up from the sign of the other side of the equation. So in particular, let's say force 1 is 24 newtons and force 2 is negative 54 newtons because it's in the negative direction. The sum of these guys over here, 24 plus negative 54, is going to give us a negative number, and that's going to tell us that the acceleration is negative because there's no way that the mass can be negative. Okay, so let's look at a slightly more complicated situation here. We've got this object. Let's say this is like a suitcase that you're dragging across the floor. You're using some force on the handle to pull it. You've got the normal force from the floor, the gravitational force from gravity acting on it. I haven't shown the floor here. And we've got some frictional force or something like that slowing this guy down. If we redraw it as a proper free body diagram, so we break these guys into components, and we've got the sum of the forces, or the mass times the acceleration in the x direction is equal to the sum of the forces in the x direction, and likewise for the y components over here. Okay, we're going to break down F1, or excuse me, the x components into the x component of F1, the x component of F2, and then the x component of the normal force and the x component of the gravitational force. Now, again, if you're paying attention, there is no x component of the gravitational force. There's no x component of the normal force in this particular situation. So we're going to get rid of those. You might do something like cross these guys out or something similar to that. But we're only left with the x components of force 1 and force 2. And then we're going to write this down as an algebra equation. When we do that, F1, the x component of it is in the positive direction. F2, the component of it is in the negative x direction. So I've got the negative sign there. If we look at the y direction, again, we write out all those forces, the y component of F1, the y component of F2, the y component of the normal force, the y component of the gravitational force, and of course, there is no gravitation, or excuse me, there's only the gravitational force in the y direction, so I can lose this subscript. I can lose that guy. I can lose the subscript on the y, and I can also get rid of the normal force on, or excuse me, the y component of the force on object 2. Okay, and then I write it down as a algebra equation. M1A is equal to the positive component of F1, and the normal force also points in the positive y direction, and the gravitational force, of course, points in the negative y direction. Okay, now in order to choose directions, you've got a couple of choices. You want to make sure that you choose a convenient direction for positive and negative, and there are two ways you might do that. Okay, a lot of times I'll do what I have over here on the right. I know that F2 is the larger number because of looking at either the wording of the problem or the picture here, and so I put the positive force in to the left, or the positive direction to the left. Or if you're more traditional and you always like to have the right direction as positive, then in this case F2 is going to be negative and F1 is going to be positive. If you don't know, because you don't have an idea of the actual numbers or the magnitudes of these sizes, then just guess. Just pick a direction, maybe make it convenient. If it's sliding down an incline, you might make down the incline downhill. If it's falling down, you might make downwards positive. That's completely up to you, but you can guess. But once you do that, mark the positive directions on your diagram, and then be consistent throughout the problem. Don't change things halfway through, because then you'll have to go back through and change the sign of everything. Okay, now let's take a quick look at an example problem. We've got these two forces acting. F1 is acting to the right with a force of 21. Another person is pulling with a force F2 in the to the left, which I'm going to have as the negative direction. So I've set my positive up top. And we want to know the acceleration of the box. Well, I've gone through my steps. I've drawn my pictures. I've drawn my free body diagram. I've written down the component or the pieces of information that I know. Okay, and I again write down the sum of the forces is equal to the mass times the acceleration as a vector equation. The y components here are going to cancel out, so I'm really only acting in the x direction. So I'm going to keep these guys all set here. I'm going to write down that algebra equation without the signs, and then I'm going to add the signs in. F1's in the positive direction, put in the positive sign. F2 is in the negative direction up here, and so I put it in the negative direction. And again, put no sign on the acceleration. Now I know in my head that this is going to end up going to the left, which should be a negative number, but I don't force that in there. That's going to fall out naturally from the math. Okay, so I do a division, divide both sides by m to get a by itself. Now I've done all the algebra that I can do. I'm going to throw in my numbers, and here the numbers are just thrown in as 21 and 52. The negative sign is coming from the form of the equation. Do the subtraction first and then do the division, and I end up with a negative number right from the algebra, negative 3.1 meters per second squared. Remember, Newton per kilogram is an acceleration, so that's meters per second squared. And then just to make sure that my physics professor understands that I understand what's going on, I'm going to actually write down a sentence. that the box accelerates at 3.1 meters per second to the left. That way I'm very clear about the direction that it's going. So this is my magnitude. This over here is my direction. Okay, now for a quick review. If you're doing a problem involving Newton's second law, always write the vector equation rather than F is equal to ma, so that you don't make the mistake of just algebraically adding or just mathematically adding force 1 and force 2, which can really be a problem if they point in different directions. So just be careful of that. Always write F equals ma with the vector sign in there. Okay, and then when possible, break it into convenient components. Usually the x component and the y component. When you're on a slope, you do something slightly different, but it's the same idea. Break it into components. And then each of these equations, break out the summations, F1 in the x direction, F2 in the x direction. You might have a bunch of other forces that you add in that x direction. Those are equal to the mass times the acceleration in the x direction. Okay, and then change the vector expressions into algebraic equations, explicitly including the signs for the positive and negative forces. And then finally, remember, you're not going to give a sign to the acceleration. You're going to let that fall out naturally from the algebra. That way, the physics does itself for you.